Welcome back, students. In this video, we're going to look at two different reactions, syn and anti-dihydroxylation. Dihydroxylation reactions are when you add two OH groups across the pi bond. Remember that syn means you're adding from the same face and anti means you're adding from opposite faces. So we're going to look at both types of reactions and consider how the stereochemistry is achieved. You have to watch out, though, for enantiomers, because for this first one, I didn't draw the enantiomer, so I'm just going to put plus En, so I don't have anything that's wrong here. But that second one is a meso compound, so it doesn't have an enantiomer. We'll talk about that more when we look at the mechanism. On the next page, before we get into these, I want to talk a little bit about this RCO3H, because a lot of times people think that's a typo. So let's dive into that really quick. That is actually not a typo. It is called a peroxy acid. A peroxy acid is a type of peroxide. Remember, a peroxide is something that has an oxygen-oxygen bond. The peroxide that you're most used to is hydrogen peroxide, which looks like this. See how here you have an oxygen-oxygen bond, an oxygen-oxygen bond. The peroxide, or the peroxy acid on the left, is a general peroxy acid. That R group can really be anything. Whereas the peroxy acid on the right is actually one that has a name. This is called MCPBA. So this peroxy acid is one of the most commonly used ones that you're going to look out for when you're seeing these reactions. Let's dive into AntiDihydroxylation. In AntiDihydroxylation, remember in anti-addition, you're seeing two groups add across the pi bond, but they're adding from opposite faces. So one is going to be wedge and one is going to be dash. Now, I've already written out the first part here. MCPBA makes something called an epoxide. If you would like to see how MCPBA creates the epoxide, you can go ahead and look that up in your organic chemistry textbook. What I want to do is look at how the acid in the second step affects your epoxide. So what happens during the course of this reaction is your epoxide is going to interact with that acid by pulling off a proton. And if you look at the epoxide, notice how it has a really similar structure to what we saw in an earlier video, which was that brominium ion. Once the epoxide pulls off a proton and becomes protonated, then these carbons that I'm highlighting in yellow become even more electrophilic, and they're much more reactive. That allows water, your weak nucleophile, to come in and attack. When water comes in and attacks, just like when you saw the brominium ion, you have an oxygen that has a pair of electrons, right? That's taking up space. It's got a pair of electrons. Over here, you have an oxygen with electrons, and these don't want to be anywhere near one another. So if your ring is my hand and the epoxide part is my other hand, the epoxide part is pointing above the plane of the ring in this drawing, so the water needs to come in opposite that in order for those two groups to get as much space and spread out during that transition state as they can to lower that energy of the reaction. Now, when the water attacks from the opposite side, my OH that was already present is going to stay whatever it was, right? It's wedge here. And the water is going to come in and attach from the opposite side. Remember, it still has that extra proton on it. This, when you have water bound to a structure, this is called the oxonium ion. Something needs to come in and pull off that extra proton, and it's going to be water molecules. And you might be thinking, wait, but where are those water molecules? Remember that acid is aqueous. So when you have an acid in your solution, you also have water present. And water is going to behave as the base to come in and pull off this proton to open this up. This is also called an acid catalyzed ring opening of an epoxide. That's long and wordy. Just catch the acid catalyzed part in there. If it's an acid catalyzed reaction, that means we need to regenerate acid at the end, which is what we're doing. Here we used an acid proton. Here, this oxygen's pulling off another proton to recreate H3O+. So we've regenerated our acid catalyst through the course of the reaction. Now, when I look at this product, remember, just like the brominium ion reaction that we just saw, what you're going to see is a pair of enantiomers here. You're going to see a pair of enantiomers because you can have equal attack or equal possibility of attack from this side as well as the route that I showed over here. And that gives rise to both enantiomers. So you're going to end up with a racemic mixture. Now let's look at the other dihydroxylation reaction. In the Syn dihydroxylation reaction, your two OH groups are adding from the same face. And the way that we're going to remember this is by looking at the beginning part of this mechanism. I'm not going to show you the whole mechanism, and I'm not going to expect you, if you're in my class, to recreate this mechanism. What happens in this reaction is your pi bond attacks an oxygen. This pair of electrons goes on to the osmonium, and then your pi bond comes in and attacks this side. That's a little crowded. Let's make that nicer. Here's the thing. This is the reason why you're getting the Syn. Because these carbons are sp2 hybridized and thus trigonal planar. Your osmonium tetroxide, which is this thing here, is a compound that is also planar because it's square planar. So you have two planar things that are coming together. Of course, they're going to create a situation where the two OHs are adding from the same side because everything is planar. So let me draw what it looks like when the osmonium tetroxide has added. And remember that when I draw these wedge bonds to oxygen, these could also be dash bonds. The reason that we have to draw them as wedge or dash now is because this carbon and this carbon are no longer trigonal planar. Right? They are now sp3 hybridized, so they are going to be wedged or dashed. The thing I want to point out to you is that the OSO4 is all connected to one another, especially this area here. That area is really illustrating that the oxygens are adding from the same face. They have to, because everything is planar. The second step that I'm not going to show you is an oxidation reduction step. And what you're going to find is whenever there's a redox type reaction where we're getting rid of some group and replacing it with something else, we usually gloss over that. And the second step, what happens is something comes in and pulls off this part so that where you have those oxygens attached, they turn into OHs. Now, if we went through and drew the product for this one, you would see that you have two OHs on the same side, and that this is a meso compound or a meso compound, however you'd like to pronounce it. And this doesn't have an enantiomer because there's an internal plane of symmetry. But that's not always going to be your case depending upon what you start with. And that's what I want to look at in the next example. In the next example, I have some other groups already attached to the pi bond. When I already have groups attached to the pi bond, your OHs are going to still add from the same side, from the same face. So let's go ahead. You can put in some wedge OHs if that makes you feel good. It doesn't matter if you use wedge or dash. And if those are wedge, that's going to force that ethyl to be dashed and force this methyl to be dashed. Now, when I look at this and I ask myself, is this a meso compound? The answer is no. There's no longer an internal plane of symmetry here because I have two different groups attached across that initial pi bond. So I have to draw both enantiomers as my products, and this will be a racemic mixture. Now let's look at all the reagents that you can use to achieve Syn dihydroxylation. The first three are all going to contain osmonium tetroxide. Osmonium tetroxide is actually really poisonous, so these first two sets of reagents, this one here and this one here, are meant to have the osmonium tetroxide and the co-oxidizing agent, the thing under the reaction arrow, in the flask at the same time, so that you can use a very, very small amount of osmonium tetroxide. Whereas this third reagent, this is actually going to be step 1 and step 2, like we saw on a previous slide. Then the final one is potassium permanganate and sodium hydroxide, and making sure that that's cold. So these will all do the same thing to get you Syn dihydroxylation. Therefore, all of these result in the same product, where you're getting an OH and another OH across the pi bond, adding from the same side, and then you're forcing any groups that are already existing across the pi bond to also be on the same side. Let's wrap up. In this video, we looked at two different types of dihydroxylation reactions, the anti and the syn. In both of these, we added OH across the pi bond, and in the anti addition, we had the two OHs add from opposite faces. You need to make sure that you're watching out for enantiomers every single time there, because it's very likely that you're going to get enantiomers. In SynDihydroxylation, you're still getting two OHs adding across the pi bond, but they're adding from the same face, which means if you have an internal plane of symmetry, you're not going to have a pair of enantiomers because you've created a meso compound. But if you don't have an internal plane of symmetry because of the way that your initial alkene is set up, then you are going to have a set of enantiomers. There are multiple reagents that you can use to accomplish Syn dihydroxylation, so just be aware of that moving forward. Thanks so much for your attention. This is Katoni signing out.